Hello everybody, my name is Federico Campoli. I am a freelance PostgreSQL consultant, and today I will talk about PostgreSQL running on top of ZFS, a powerful file system but with a bad reputation. So if you are a sysadmin or DBA and you are searching for an alternative for performance and scaling up your system, you may be interested in my presentation. Thank you. Okay, so let's start with the Vindicating ZFS with PostgreSQL, unleashing the power of scalability. Before I start, I want to present you a little about myself. I look younger, but I was born in 1972. I am passionate about IT since the 1985. I'm in love with PostgreSQL since 2006, and I have a PostgreSQL and FreeBSD tattoo on the right shoulder. Not sure if it's visible, but I can show you there. So I am one of the two crazy people to tattoo PostgreSQL on our skin. So I am a freelance DBA. So let's talk also the way to get in touch. This is my LinkedIn account. This is my GitHub page with some of my projects. I'm also an amateur Python developer. This is my SoundCloud. This is contains mostly of my experiments with music, because I'm also an amateur jazz guitar player. And this is my blog. It's not exactly up to date, but I promise I will resurrect sometime. So let's talk about this particular talk. The talk is based on a real-life experience. Of course, I cannot show you the information about the customer because it's reserved information, is under NDA after all. But I did some reenactments of the tests I had with the customer on a different platform, different environment and different volumes, but they are quite interesting. There are a lot of topics not covered by this talk. The time is quite short for presenting this thing, so I'm not covering entirely the ginormous amount of information you can get on ZFS. So consider this talk, as this presentation, as a starting point. So I want to stimulate your curiosity and maybe give you an alternative to the normal solutions you can find on Linux. And most important, always test before going in production. Things may vary a lot from one case to another, and I also discovered that the tests are are even better than the tests made at the customer. So always test before going into production. So our agenda, our table of contents is quite short. We are doing some context. So what happened to me when I worked at this customer. The key master and gatekeeper is a quote from the probably the most hilarious movie after Frankenstein, Young Frankenstein, in the world, so Ghostbusters. Some tests and some wrap up about the situation, the discovery we had through our tests. So the story about that you are about to hear is absolutely true. Names and other stuff are being changed to protect the innocent. So take this information as based on a real story. So what happened? This time happened probably 1.5 years ago. A long time ago, there was a startup far, far away. And that was running this Postgres on someone else's computer, also known as the cloud. And this database was misused, abused by the developers. And the result of this misuse, it was causing a massive bloat on this database. This is one of the problems we have in Postgres. The architecture of PostgreSQL is expose the storage to become bloated if it's not correctly understood, if it's not correctly used. And that was exactly the case. It costed a lot of money to the customer because the storage required an extra expensive storage class. So they called the DBA, me, and as my usual, I may look quite nice or funny, but sometimes I get incredibly harsh. And this is my approach when I get the problems. So this is Sparta. I usually start teaching out, screaming, and trying to find a solution because things should be correctly configured to make the database. Blaming the database, blaming PostgreSQL is not the correct way to approach stuff. So we had a lot of possibilities. We explored a lot of possibilities, and one of those possibilities was ZFS. Now, before talking into ZFS, let's talk about the fact that Postgres and Linux are not friends. Well, why they are not friends? Because there are two systems that are based on different paradigms, different architectures, and they were built on different starting points. For example, in PostgreSQL, we have a multiprocessing system. So PostgreSQL is not multi-threaded, but is multiprocessing. The block size, the default block size you may find into the normal installation is 8K, 192 bytes, and is allocating when you started our infamous and our friend, the shared buffer. It generates one big shared memory segment. So expect that the memory is contiguous into the RAM, and it consumes a lot of memory. So what's the problem with Linux, our gatekeeper? Well, the Linux infrastructure is based mostly, the modern Linux infrastructure uses NUMA, and that means the memory pages are scattered around RAM. So when you allocate the shared buffer, it's not guaranteed that the shared buffer will stay in one contiguous segment. There is a way to force this behavior. The max file system block size on x86 architecture, so AMD or Intel, is limited to 4K. So it means half of the block size of PostgreSQL. So it means fragmentation. Dirty flash on Linux, the dirty flash is something that happens when you have a lot of writes to be flushed on disk into the kernel memory. When a dirty flash synchronous I/O happens, it blocks the I/O, and it seems like the database is blocking, but it's not the database, it's Linux that is blocking the database I/O all together with the rest of the I/O on the operating system. And there is our friend, the infamous OOM killer. The OOM killer. OOM stands for out of memory killer. So basically Linux tends to over-allocate, over-commit the memory. And this is, from a database point of view, is a bug. So Linux is not optimized for working with the database. But they can be gently pushed together and summon Gozer, basically. So how can we do that? We need to work on both areas, our keymaster and our gatekeeper, Postgres and Linux. In terms of PostgreSQL, we need to tune the max connections. Do not consume too many connection slots. Enable the usage of huge pages. The huge pages is a way for telling PostgreSQL to use an infrastructure implemented in Linux that permits to have a single shared contiguous memory segment into the RAM. do not oversize the shared buffer. This is a particular point I've seen several times, in particular when working on cloud-managed databases. The shared buffer, after a particular size that is around 64 gigabytes, impose regression, it creates regression, not improvement. So do not oversize the shared buffer for another reason. The shared buffer is designed for optimizing the access on blocks, but the segments, the file segments are well managed by the Linux kernel cache. So let's work in tandem between the shared buffer and the Linux kernel cache. Do not allocate the entire memory to the shared buffer, because this is not going to work well. On the Linux side, disable or make NUMA less probable. Configure and use the huge pages, because you can tell Postgres to use the huge pages, but you also need to tell Linux to allocate a huge page sufficiently big to contain the shared buffer we want to set. And also configure the VM dirty ratio. This is the percentage of memory into the kernel cache that triggers a synchronous flash on disk, a blocking flash on disk, when is reached. The default value is very low. On some Linux is 20%, on another Linux is 10%. It depends by the distribution. But this value is absolutely dangerous, because it may end up with a large shared buffer in particular. It may end up with a blocking I/O on Linux. Disable the memory over commit, and disable the memory over commit is mandatory on database systems, and on supported architecture, set the file system to block size 8K. This is possible on ARM architectures. Or use file system more flexible like ZFS. And now we go into the file system part. So in the normal, we are discussing about XT4, but some of the concepts apply also to XFS. So in XT4, it's possible to optimize the file system at mount time. So disabling no A time, no dire time, it gives improvement when accessing the files, because the system, it won't need to update the access time for the files when accessed. So better performance. We can disable the barriers, the write barriers, skipping a little the safety for having more performance in write. My recommendation, and also the Red Hat recommendation, my recommendation about do not disable the barriers on the WAL area, and the Red Hat recommendation is do not disable the barriers on virtual machine disks. So because we are on virtual machines, we are not using the barrier 0. Using also data write back for the journaling improves the writes on XT4. So why considering ZFS instead of XT4? Well, because XT4, ZFS, it creates a massive architecture, a massive infrastructure for our system. In fact, it's more like a database rather a file system. I like it a lot, even because some of the concept I found into PostgreSQL, I get the same concept into ZFS. So in particular, we have a pooled storage, we have the copy on write, we have the snapshots, we have the data integrity and verification and automatic repair with the scrubbing. We have an implemented and a built-in RAID when we have multiple devices, is RAID Z, and we can store up to 16 exabyte file size. And we can have 256 quadrillion zettabyte in storage with no limit of the number of file system datasets. Well, it's just numbers, just the upper limits. Of course, the limits that are imposed by the resources. The cons of ZFS. The license is not compatible with GPL, so it's not part of the Linux distribution. You need to install separately. It's memory greedy. It's basically a database, so it's memory greedy like any other database. The maintenance requires attention, is not very efficient in writes, but it can be improved. And there are some bugs that are popped up. In particular, this one is pretty horrible because under particular conditions, it can lead up with data corruption and loss. So always be up to date to the release notes and the mitigation if something comes up into the system, into the release. This applies on anything, not just the ZFS thing. Options for ZFS. Another good thing about ZFS, you can hot configure ZFS. So you can, instead of applying the change, remounting the system, and maybe get some downtime because you had to shut down the database, remount, and so on. In ZFS, you can change these settings on the fly. Of course, the changes apply only to the newly written data. So you can set up the A time, disable on or off the access time, similarly to the XT4. You can change the record size. Record size stands for block size in ZFS. The default is 128K, but you can change it accordingly to your needs. You can enable or disable the compression, transparent compression. The default is LZ4, is gzip, and you can also use different algorithms like LZ4 or ZSTD. ZSTD, yes. You can set a log for the intention log for having a preemptive way to managing the ZFS itself. And also you have the possibility to configure the ZFS module, because it's a module, it's not part of the Linux kernel. You load the module and you set your parameters. You can persist the modules into the modprobe.d, but you can also write most of the parameters as a dynamic value using this format. So, as a last part of this presentation, let's do some tests. Because back in my day, we had only 640 kilobytes, and I'm old enough to remember that my first computer had 4 megabytes, and it was a huge amount of memory. Anyway, this is the system I used for the test. So I created on GCP an E2 IMEM28 with a Rocky Linux 9.3 and 4 attached storage systems, all SSD. One for the data area and WAL area. So I removed the I/O caused onto the WAL from the equation. So the other table spaces, XT4 and ZFS, are completely independent. And also I added an SSD with the ZIL, the ZFS intention log. The system used for the test. The hardware is a Google Computer Engine IMEM8 with 62 gigabytes installed RAM, 8 processors, AMD EPIC 7B12, separate volumes as shown into the diagram, the XT tablespace on SSD, ZFS on SSD, ZIL on SSD, and no swap area. The kernel and the Rocky Linux, it was the 9.3. Rocky Linux is one of the distribution rebirth from the ashes of CentOS, basically. Kernel configuration: dirty background radio and dirty radio set to avoid any weird flash I/O. Dirty background radio, it keeps the flashing background constantly in background. The dirty radio makes very difficult to have a blocking I/O. The VM overcommit memory disabled, the overcommit radio 100, swapping is set to 0. Postgres setup, Postgres 16.2, shared buffer 1 gigabyte, work mem 400 megabytes, max connection 100, and max WAL size 5 gigabytes. Using pgbench with the default, scaling factor 500, with 50 million rows on pgbench account, 500 rows on branches, and 5,000 on tellers. Number of clients 50, and one number of threads 1. Duration of each test 120 seconds. No foreign keys to disturb the operation. So pgbench initialization for each test. So the tables are recreated every time. So On XT4, the creation, it takes about 18 seconds. And after the run, we get this value, TPS 4900 transactions per second. Disabling the adding the no wait time and no zero time, it makes the operation slightly faster. The TPS jumps to 5300.72 and 71. Also, changing the data to write back improves it makes things slightly worse. So it makes basically no change. The value is similar. There's some fluctuation, but there's no big difference anyway. Let's see instead our friend ZFS. Now, on ZFS, with the initialization with no tuning, the TPS is 1700s, is horrible, the performance, and it explains well the bad reputation of ZFS. But with A time off, so turning off the A time for that dataset improves a little, but we are still on what the... So how can we improve this thing? Well, at the customer, we try the compression using different compression algorithm. The first thing noticed is that the space used dropped from 7.4 gigabytes to less than 1 gigabyte. And also, the performance in terms of TPS, it jumped a lot. It becomes slightly worse than XT4 with no tuning. So we are getting better space and better performance. But we can improve this thing? Yes. We are still using the default block size, the default dataset size, record size. So if we set the dataset to 16K and we get, more space allocated, so less compression in place, what we get on GCP is TPS 6200s, better than the best on XT4. We can improve things. Yes, we can play with other parameters like the ZFS modules, disabling the flash, fixing the size of the ARC, disabling the TXG timeout. We can do this sort of stuff. Also adding the ZIL. But on my tests, the improvement was basically not measurable. The time, the number of TPS, even with this optimization, is still stay the same. Now, let's give you a quick display about the results. So in terms of space usage, the best is when we use ZFS with LZ4 with the default block size. With the in terms of load time, the load time is not very fast. The best probably is still on this thing, no A time and LZ4. So if we want to optimize our ZFS table space for batch load, maybe we want to consider this particular option. In terms of latency, the best results are found on ZFS with no A time with a record size 16K. The latency between the not optimized and the optimized with ZIL are basically similar, so there's no big difference. And in terms of transaction per second, the best are, the winner are with the record size 16K and the compression enabled on LZ4. So we are almost at the end, so let's wrap up. We can get good performance on ZFS despite the bad reputation. We need to look after any weird bug appearing and always use the PostgreSQL block checksums and always use the right tool for the right job. So no ZFS if you have a 20 megabyte database, and always RTFM. This is very, very important. And finally, remember that your mileage may vary. This is a picture of the best car even built, the Panda 4 dry wheel. Is unstoppable, but he has no airbag because we die as heroes. So we are at the end of the presentation. I hope you can get it as a starting point. And that's all, folks. Any question, please?